In acoustic engineering, what you consider noise is completely irrelevant. One person's heavy metal is another's headache, making subjective assessments useless for real-world design. Instead, engineers measure sound objectively as a physical pressure wave, specifically the sound pressure level, or SPL. When tasked with stopping these high-pressure waves, our first instinct is usually brute force. We assume that if we just build a thicker, heavier wall, the sound won't be able to punch through to the other side. This diagram illustrates the physical limits of that approach, governed by the mass law. Because of diminishing returns, taking a solid 3-inch concrete wall and doubling its thickness to a massive 6 inches yields only a measly 5 decibel increase in acoustic isolation. To achieve professional-grade silence, you cannot just pour more concrete. You have to abandon the illusion of brute mass and outsmart the physics of the wave itself. This graph charts a wall's transmission loss. On the far right is the coincidence effect. When incoming sound wavelengths match the wall's bending waves, it creates an acoustic hole, plummeting isolation performance by 10 to 15 decibels in the critical mid-range. To stop a wall from transmitting and amplifying these waves, engineers use a technique called decoupling. Instead of pouring one thick slab, they split the wall's mass into 2 independent physical leaves, separated by air. Solid wood studs act as rigid acoustic bridges, directly conducting vibrations. By alternating the studs on a wider base plate or using flexible metal resilient channels, the physical bridge is broken, forcing sound to travel through the airspace. But solving the direct structural vibration transfer creates an entirely new problem. By introducing that internal air gap, the wall accidentally transforms into a highly efficient acoustic trap.
Splitting the structural frame introduces mass-air-mass resonance. The trapped air between the independent drywall leaves acts like a mechanical spring, dynamically coupling the separated masses back together. If you build both sides of this wall out of the exact same material with the exact same thickness, they share identical resonant frequencies. When sound hits that specific frequency, the 2 leaves oscillate in perfect sync, severely magnifying the sound transmission right through the air spring. This diagram shows the countermeasure, dissimilar mass. By installing double drywall on leaf A and single on leaf B, engineers offset the resonant frequencies. Finally, packing the cavity with fiberglass provides damping, absorbing sound waves without reconnecting the walls. By decoupling the frame, varying the mass, and damping the cavity, engineers create a dynamic barrier that actively neutralizes acoustic energy. Acoustic energy behaves remarkably like a pressurized fluid. If there is a single unsealed crack, keyhole, or split in your perfectly engineered wall, the sound wave will exploit that tiny pathway to leak completely through with absolutely zero transmission loss. This is why a standard residential door completely compromises a soundproof room. A typical hollow core door offers barely 15 decibels of practical attenuation, essentially acting as an open window for low and mid-frequency noise. High-performance acoustic doors require extreme exterior engineering. They start with thick, solid cores made of heavy particle board or plywood. To maximize internal damping and add sheer limp mass, manufacturers will even physically fill the hollow frame of the door with dry sand. But even a heavy, sand-filled door is completely useless if air can travel around the edges.
A true acoustic barrier requires sealing the entire perimeter using heavy, compressible neoprene gaskets and specialized mechanical drop bars that automatically plunge down to seal the floor gap the exact moment the door closes. For absolute isolation, industrial designs borrow technology directly from refrigerators. They use a magnetic polyvinyl chloride gasket lined with barium ferrite. The magnet forcefully pulls the heavy door leaf against a flat, mild steel frame, guaranteeing a high-pressure, totally airtight closure. Complete silence is never achieved by one single massive object. It is a fragile, interconnected system where structural decoupling, complex resonance mitigation, and absolute perimeter sealing must all operate in perfect unison.